Hello everyone, welcome to my channel. In this video, I'll be evaluating the famous Gaussian integral, which is the integral from negative infinity to positive infinity of e to the power minus x squared dx, as you can see here. Now, this is one of the most difficult integrals that you will all have come across. There are many techniques, what we call non-elementary techniques of evaluating this integral. In this video, I'll be using the transition from rectangular coordinate system to polar coordinate system, and this transition is known as the Jacobian, and I'll be explaining to you what the Jacobian is shortly. So let's start then. How do we go about this? Well, a simple technique at the beginning, but as we go, you'll realize that it's not an elementary approach. So let's start then. Our solution is, let's call it I1 for I for integral. Integral 1 is basically the integral from minus infinity to positive infinity of e to the power minus x squared dx. Now, like I said, this is not an easy integral. And so right from the start, how do we go about this? Well, we're going to square both sides. So I square I1 squared. I take I1 and I square it. It will be taking the entire integral from minus infinity to positive infinity of e to the minus x squared dx. And I have to square this. Well, on the left, I just get I1 squared. On the right, I'm going to get a repetition of this. So the integral from minus infinity to positive infinity e to the minus x squared dx, multiplying by the integral from minus infinity to positive infinity of e to the minus x squared dx. Now, considering the fact that x is a dummy variable, in other words, you can actually change it to any other variable, because this is a definite integral where we have limits of integration indicated from minus infinity to positive infinity. In other words, integrating this expression over the entire x-axis. And therefore, the right-hand side here, we can change the variable in the second part to x, to y. I'll show you why we do that shortly. So this change is the same as the integral from minus infinity to positive infinity of e to the minus x squared dx, multiplying this by the integral from minus infinity to positive infinity of e to the minus y squared dy. Right, like I told you, x is a dummy variable, so we can change from x to y. Now, looking at this part here and understanding that we're integrating from minus infinity to positive infinity in both cases, we can combine these two functions here, forming what we call a double integral. So this will be the integral from minus infinity to positive infinity, integral from minus infinity to positive infinity of, watch this, e to the power minus x squared times e to the power minus y squared dx dy. So notice that dx dy implies the inner part, the inner integral. This first integral here will be with respect to x, and the second one, the outward one, will be with respect to y. Now, using laws of exponents, you remember same base, we add the exponents. Taking us to page 2, so we're going to basically say now that our integral, double integrals, will change to the integral from minus infinity to positive infinity, from minus infinity to positive infinity of what? Of e to the power minus x squared. If you like, we're adding the powers, so it will be, if I use brackets, plus y squared like that. And then we have dx dy. Hopefully you catch that. Right. Maybe I should get a separate page here, just quickly, because it's quite a process to go through this. I'm basically saying e to the power minus x squared times e to the power minus x squared and minus y squared. What do we do here? Same base, we add the power. So it will be e minus x squared plus minus y squared. And what is this? Well, this is e to the power minus x squared minus y squared. If you factorize that, take minus 1 out, you're going to get e to the minus 1 x squared plus y squared. This can also be written in short as minus x squared plus a square like that, e to the power minus x squared plus y squared in brackets. That's what I'm trying to say here. Now, looking at this part here, x squared plus y squared, it should take us to, let me just inject this one in here right away. It should take us to the Cartesian plane. We are focusing on a circle of radius r through an angle of theta. If we form this right angle triangle straight away, this distance here is going to be x, from there up to there, and then from up there up to there, let's call it y. From here, it is very clear that x squared plus y squared equals r squared by Pythagoras theorem. So that's Pythagoras theorem. Some people say the theorem of Pythagoras. Now, this is first result. So we understand that this part here will be replaced with r squared. But what about dx dy? Well, dx dy takes us to what we call the Jacobian. Now, the Jacobian comes from two equations that we obtain from this right angle triangle here. And I want to form them from over in this space here. Remember, x over r equals cosine of theta. So x over r equals cosine of theta. And therefore, x will be equal to r cosine of theta. First important equation. And also we have y over r equals sine theta. And there sine theta, not sine alpha, sine theta. And therefore, y equals r sine of theta. Now, these two equations are the equation we're going to use to obtain what we call the transition from rectangular coordinate system where we're using x and y to polar coordinate system where we're interested in the angle and radius. Now, the Jacobian basically says we have dx dy, the connection between dx dy is equal to the Jacobian times dr d theta. Now, we're interested in working out what this transition Jacobian is, J. Basically, if you watch my videos on linear algebra, I've explained what a determinant is. We're going to work on a determinant of a 2 by 2 matrix. Let me show you shortly. We're coming back to that integral there. Now, let me take this to page number 3. So, basically, we are saying that, yeah, you can see that, yes. So, basically, I'm saying our Jacobian J is basically going to be equal to, watch this, the determinant. We have two equations that we're focusing on there. X equals r cos theta and y equals r sin theta. The partial derivative of x with respect to r times, this will be the first entry in the first row and first column, and then the partial derivative of x with respect to theta, and then in the second row, first position, the partial derivative with of y this time with respect to r, and in the second position we're going to have the partial derivative of y with respect to theta. That determinant is what we call the Jacobian. Now let's differentiate partially x with respect to r with respect to r, differentiating this equation here, differentiating x with respect to r partially. Of course, that means we are going to treat cos theta as a constant. And when we turn around and we differentiate theta, x with respect to theta, we're going to treat r as a constant. So the derivative of r with x with respect to r, remember the derivative of r is 1. So it's going to be cos theta because cos theta is a constant. So in the first position here, we're going to have this one here, cos theta. And then we differentiate partially x with respect to theta, keeping r constant. So it's going to be r times minus sine theta. Remember, the derivative of cosine theta is minus sine theta. So we are going to have minus r sine theta there in that position. Then we're coming down. I hope you can see it. Yes. So we're coming down here. We're differentiating this one here partially with respect to r. We treat theta as a constant. So dy, partial derivative of y with respect to r, is going to be just sine theta because r, derivative of r is 1. So it's going to be sine theta. So here we have sine theta here. Differentiating partially y with respect to theta, keeping r constant, it's going to be r cos theta, because derivative of sine is cosine. So we have r cosine of theta in that space. So we work out the determinant of this, and remember this is a 2 by 2 matrix, 2 rows and 2 columns. Now remember what I told you on determinant in the previous video. I told you that you multiply elements on the right diagonal, subtract the product of elements on the left diagonal. So that's your right diagonal and that's your left diagonal. So we're going to say cos theta times r cos theta. You agree with me that this is r cos squared theta, and then minus the product of elements on the right diagonal, on the left diagonal. So sine theta times minus r sine theta is going to be minus r sine squared theta. Now simplifying this, it's going to be r cos theta cos squared theta plus r sine squared theta. Factorizing r, taking r out, you're going to get r cos squared theta plus sine squared theta. And you remember that this is 1, so we're just going to have r times 1, and our answer is r. So that's the Jacobian. So it means that at least now we understand that dx dy must transition to r dr d theta. Let me just write here. We're saying therefore dx dy is equal to r dr d theta. Wonderful. So we understand now that in this integral here, this will be replaced by r squared from there. You can see it, right? And that part there will be replaced by r here from the Jacobian r dr d theta. That allows us to transition from rectangular coordinate system to polar coordinate system. Now we have another problem. The problem we have now is that the limits of integration are from minus infinity to plus infinity in both cases. But remember, the inner part corresponds to integral with respect to x, but in this case now it will be integral with respect to r, because r will be inside. Let me just change this and then work on the limits shortly. So this integral then will change. Remember, we're coming from I squared there, I1 squared. Here it is, I1 squared. We're coming from there, I1 squared. So I1 squared is equal to this part here. Now we're changing this. If I call this asterisks, I'm going to say here on page 4, I'm going to say therefore asterisks becomes I1 squared is equal to the integral. Let me keep the limits the way I'm not indicating the limits. I will indicate the limits shortly. And then I have e to the minus r squared. Excuse me. And then we have dr dr d theta, like I told you. So now these two have been replaced. This is e to the power minus r squared, r dr d theta. Perfect. Now limits of integration. Remember, x, we're integrating x from minus infinity to plus infinity. But now we're talking about r. So think about r. It will have to be from 0. You'll have to extend this circle now so that its radius is infinity, because we're covering the entire space. So the limits of integration for r now will be from 0 to plus infinity, the inner part, so 0 to plus infinity. Now we're coming to the angle theta. If you're integrating the whole space, theta will have to move from 0 all the way to 2 pi, which is 360 degrees. So we're now moving from 0 all the way to 2 pi. Now the integral has been totally transformed using the Jacobian from the rectangular coordinate system to polar coordinate system using the Jacobian. As you can see here, we worked it out on page 3 using partial derivatives. Right, now this integral is easier now to evaluate. As you can see, we're now going to use u substitution. So we're going to say now so we're working on the inner part, that part there. Let's say let I2 excuse me, let I2 be equal to the integral from 0 to plus infinity of e to the minus r squared, and then we have r dr. Now this is the part where we're going to say let u be equal to minus r squared, that part. And therefore du, you'll agree with me that this is going to be minus 2r dr, but I have r dr here, so minus 2 must go. I'm gonna have to say du over minus 2, and that will be r dr, r dr. Now, so let's transform this then. What about limits? What about limits? Notice when r approaches 0, u will also approach 0. When r approaches positive infinity, u will approach minus infinity. So now the integral then changes. That integral changes to I2 is equal to, from 0 to minus infinity, of what? Of e to the power, remember r squared is u now, and then instead of r, the r is, we're going to have du all over minus 2. Take minus 2 out, it's going to be minus 2, the integral of 0 to minus infinity of e to the power u du. Now, remember this is an improper integral because of the minus infinity. We're going to have to use a limit approach here. So I'm going to say this is going to be the same as the limit minus 2 times the limit. Let's use the variable t. As t approaches minus infinity, of the integral from 0 to t of e to the power u du. Now we evaluate this, and then we take the limit as t approaches minus infinity of that. Now let's go to page number 5. I told you this is a non-elementary integral. The approach is quite sophisticated, but I hope you are following. So moving down here, we're going to say minus 2. Taking the limit of that, remember the integral of e to the power u is just e to the power u. And we're taking the limit of this as t approaches minus infinity. And we're saying from 0 all the way up to t. Remember 0 up to t of that integral. Now let's put in the limit. So we're going to have now minus 2, and I'm going to take minus 2 out. I'm going to do this. And we're saying the limit as t approaches minus infinity of what? Of u to the power, of e to the power t, and then substitute 0 there. It's going to be, if you allow me to use another bracket here, put 0 now there, it's going to be e to the power minus, obviously we're subtracting e to the power 0. Now, what are we saying? This is minus 2 times the limit as t approaches minus infinity of e to the power t minus 1. Now, notice something here. As t approaches minus infinity, this part here, e to the power of t, will approach 0. So we're having now minus 2 times 0 minus 1, if you follow what I'm saying. Take this out, the answer is going to be, it's actually minus, I'm making a mistake here, it's minus half from there, you follow. It's minus half, not minus 2. Minus half, sorry about that. It's actually minus half there. I was too fast there, I took minus 2 out instead of minus half. So this is minus half, and minus half, and minus half. Luckily I saw it quick enough, otherwise we would have landed into trouble. Now you can see from here that it's actually minus half that comes out, not minus 2. So minus half, minus half, minus half. Finally here our solution is going to be positive half, because minus half times 0 is 0, minus half times minus 1 is positive half. So what are we saying then? We're saying over here the inner part now becomes positive half, so we're going to have the integral from 0 to 2 pi of half d theta. So now we're saying, therefore, what we have is I1 or squared is going to be the integral from 0 up to 2 pi of half d theta. And you understand half is a constant, take it out, and therefore we have the integral from 0 up to 2 pi of d theta. And the integral of d theta is just theta. So now we have, let's move to page 6 here. Moving to page 6, page 6. Now we are saying basically that I1 squared is equal to integrating, like I said, the theta here. If you like, there's a 1 here actually. Integrating 1 with respect to theta is just going to be theta. So we're saying theta, outside we have half, and the limit of integration will be 0 to 2 pi, like that. Now that means we have half outside, and then we are saying put 2 pi there, it's 2 pi, 2 pi. If you put 0, it will be minus 0 there. We're subtracting upper and then lower when we substitute. This is actually equal to pi, because you multiply half by 2 pi, you get pi, half by 0, you get 0. So we are basically now saying I1 squared equals pi, I1 squared equals pi. And therefore, if you take square root both sides, the positive square root, that is, you're going to have I1 is actually equal to square root of pi. There you have it, ladies and gentlemen. And therefore, what are we saying? Let's go back to our starting place where we started with the first integral there. We're basically saying that this, because I1 equals this, we're basically saying that the famous Gaussian integral simplifies to that story there. So we can say, therefore, the integral from minus infinity all the way to positive infinity of e to the minus x squared dx is just basically equal to square root of pi. So we have been able to evaluate this by using, like I said, the transition from the rectangular coordinate system to the polar coordinate system, and that transition we call it the Jacobian. And here it is, basically taking advantage of this part here, these two equations here, differentiating x and y partially with respect to r and theta, forming a 2 by 2 matrix, which is this one here. And then we had to work out the determinant of that to produce what we call the Jacobian, which allows us to transition from the rectangular coordinate system to the polar coordinate system, like so, thereby allowing us to transform the entire integral from rectangular coordinate system xy to polar coordinate system, which is on this page here, page 4. And you can see here clearly that this one was easy to integrate, and we managed to do that through simple use substitution and perhaps taking limits, as you saw it, taking limits, because that's what you do when you're dealing with improper integrals, is to use limits. That's the proper way. I know some people just put in minus infinity there and say it's equals 0 in this place, but the proper way is to use constant variable like this, and then you say that a variable approaches minus infinity, and then you work out the limit. Right, so this is how you deal with this. There's another technique called the Feynman technique. I may come another video to show you how you evaluate the same integral by using another technique. There are actually many techniques that you can use, but the easier one, maybe I would claim that the easiest is this one that I've displayed here, transitioning from the rectangular coordinate system to the polar coordinate system using the Jacobian. All right, I am going to stop here. If you're new to this channel, please support us by subscribing, sharing these videos with friends. It will go a long way in helping us grow the channel and develop and produce as many videos as possible to support as many students as we possibly can. All right, see you next time.